If you think about AWS's initial service offering, it was storage, it was S3. And once you have the data, you can start to do things on top of it and you don't need to move it somewhere else.
Welcome to It's About Data, episode 80. Our guest this time is Andy Pernsteiner, Field CTO at Vast Data. Welcome, Andy. It's great to have you here. Why don't you briefly introduce yourself and your company?
Hi, Andy Pernsteiner, Field CTO at Vast Data. I have been with this company approximately 8 years now.
Okay, congratulations. And actually, another congrats is really in order here in terms of that. You folks recently completed a Series F round. I think you raised, was it about $1 billion, but more to the point, it tripled your value, more than tripled your valuation to $30 billion. And you're kind of a counterpoint because basically the 2010s were the era of the data companies, and this is supposed to be the era of the AI companies. And I know you're going to tell me you're an AI company. Everybody's going to tell me that. But
I'm not going to tell you that.
Okay, sounds good. Finally, someone goes on record here. We don't do AI. No, I'm sure you do. But anyway, I've got a couple questions I'd like to open with, which is one, you folks, started life really as a storage company, and you've kind of gone up the food chain there. And so what I want to ask is, in terms of where you're going, do you see yourselves as in your path to basically analytics and AI, do you see yourselves as a storage company or a data platform company, or a company that's become a data platform or database company?
Well, there's a lot of different things to unpack there, but I think what we're focused on is making sure that the layers of infrastructure and software required for people to process and analyze large amounts of data, that's where we live. We live in the layer between the hardware and where people are generating insights. And so if you think about what's required to do that, in terms of if I have data, I'm a customer, I have data and I want to learn something from that data, I need it to go somewhere. And oftentimes that means I need a place to store it. But I don't need to just store the raw data. I need to store the derivative data, meaning the structured metadata or information that I learn about the data. I need a place to put that. I need a way to do the processing, which means I need maybe some models or I need some functions or pipelines that run. I need a place to run those. I need compute. I need GPUs. I need networking. I need all the pieces in between. And I need to do it in a way that allows me to rapidly innovate and not have to spend time finding where all my stuff is. And so, where we focus most of our energy is making sure that we take the raw components that are hardware, the networking switches, the SSDs, the GPUs, the CPUs. We create a software layer that allows for those to be aggregated and used at scale to process and store large amounts of data.
Let's double down on that, because I think this is really where we're cutting to the chase, which is what you folks do. Shared nothing was sort of the thing of the 2010s. That was basically the conventional wisdom for scale out. But you go a very different direction, which is shared everything. And I think you were just cutting to the chase there. So tell us basically, how that basically, not just how that makes you different, but what's really the practical impact of that, and why it makes your architecture more efficient, for processing ridiculous, torrents of data.
Yeah, I think, well, a lot of the people I work with, including myself, worked in the world of what people call shared nothing storage architectures, where you have servers that are owning or in ownership of some amount of the data. And we ran into lots of challenges while working at those different companies or working for those different technology vendors, because as those systems scale, they have breakdowns. And the breakdown happens because in a shared nothing architecture, every server owns some amount of SSDs or hard drives. It owns a portion of the data. And if it goes away, then there is a portion of the data that needs to be recovered from or repaired. And anytime anything has to happen on the system, like a repair or recovery, there has to be a lot of what we call east-west traffic between these servers. So let's just play a silly game. Let's say I'm a server, let's say Matt's a server, and Tony's a server. That means if I die, I don't want to die, but if I do die, that means now all the work is on you. And not only do you have to retain the rest of the workload, you have to do extra work to recover from the loss of me. Now, that's if there's a failure, but even when there's not a failure, let's imagine that it's me, you, and Tony, and when data is sent to us, let's say it's sent to me. In order for me to make sure that it's persisted and stable, I have to talk to you. And sometimes I don't want to have to talk to you. Sometimes you're busy talking to somebody else. And so it takes you a long time to respond to me. And that means whoever's sending me data is waiting for me to talk to you. That's basically what a shared nothing architecture is. It's a bunch of servers needing to talk to each other to complete normal work, and it gets in the way of what the actual end user applications need, right? And so as those systems scale, it means now I have to talk to a lot more. There's not just three of us in a room. There's 100 or 500 or 1,000 of us, and any one of the points in that chain, any one of the servers in that infrastructure, if it fails, or sometimes even worse, if it doesn't fail but it acts slowly or is slow to respond, it makes everybody else take a long time to do what they need to do. And so that's where shared nothing architectures break down. Vast, looking at that, needed to come up with a new architecture. And actually, a lot of the reason why we came up with the new architecture wasn't only to solve for the problem of scale, it was also to solve for the problem that we were trying to drive down the cost of infrastructure, because we ourselves do not sell the hardware associated with the infrastructure that customers need to deploy. So we have no incentive to have the customers buy more hardware. We actually want them to buy less hardware because that reserves more of their money to be able to spend on software. And so our goal is always to reduce the cost of the hardware. And the way to do that is to come up with new architectures. For example, in a shared nothing architecture, you need to provide the ability to fail one or more servers, which means you need to shorten or narrow your stripe width, meaning the data that gets written across all of those servers needs to have a stripe. And a lot of people think about erasure coding or RAID, but effectively, the stripe that you can have on a shared nothing architecture is relatively limited. Most of the systems that I've seen, they max out at what's called like a 16+4 stripe, which means about 25% of the actual capacity of that system is wasted on overhead, meaning you can't use it. That's expensive at scale. That's expensive, especially if you're using SSDs at scale. And so our goal was to reduce the cost of ownership of being able to deploy large scale amounts of data storage. And the way that we did that was we came up with our own erasure coding stripes using what we call as a shared everything architecture. In a shared everything architecture, me, Matt, and Tony, we don't own any of the SSDs. We all get to share them. And all those SSDs are typically parked in servers that have no intelligence whatsoever. We have intelligence, but the servers don't. The servers that own the actual SSDs don't have any intelligence because we don't want them making decisions. And so whenever data comes to me, I don't need to talk to you. I can write it directly down to that SSD or NVMe layer using something known as NVMe over Fabrics, which is effectively the ability for a server, such as myself, to be able to access SSDs remotely as though they were local to me. And because we've created a software platform that allows for all of us to share all of the SSD state layer, it means that if one of us dies, maybe you get sad, but you don't need to do extra work because I went away. You never needed to talk to me in the first place. So why should you need to talk to me now? Right. And so what that gave us was the ability to create much wider stripes. For example, we have a 146+4 stripe, which is approximately 3% for overhead. 3% versus 25% is pretty significant when you have 100 petabytes at scale. There's a lot of other nuances that shared everything gave us. One of them is obviously failure resiliency. Another is more efficiency from an erasure coding standpoint. The other thing that allowed us to do, which kind of ties into all the other things that we've been doing, is it means that we can separate the performance from the state layer. We can separate the performance of the applications from the actual state layer or the storage layer, which means that maybe on day one, me, Andy, I'm a server in a vast cluster. I'm only doing storage related activities. I'm only allowing people to copy S3 objects or NFS files or SMB files to me. But then one day, maybe the customer workloads change, the use cases change, and they want to allocate servers to focus on database related activities. Well, because there isn't a direct relation between the storage layer and the compute layer, you can be more flexible on the applications you can stack on top. So we can manage services on top much more easily than you could if we were in a shared nothing architecture. Because again, if you look at all the historical shared nothing architectures, we'll take Hadoop, for example. HDFS is a file system of sorts where every server owns data, but every
Mm,
server is also doing a lot of work. It's running MapReduce jobs, it's running Hive queries, it's running, you know, lots of different applications. But if one of those servers dies because one of those applications is overloading CPU or memory or something, then it affects the file system. That's not good, right?
hmm
But in our world, if I'm running too much and I get overloaded, the worst that happens is that the people who talk to me, meaning the applications, that they experience some slowness, they can be redistributed somewhere else. But if I die, it doesn't affect the storage layer. Nobody else gets affected, right? And so that allows us to keep scaling and add more
hmm
use cases and applications on top. And that's why we have customers today who started, as you mentioned earlier, with storage, with storing large amounts of data. But now they're starting to take advantage of more of the applications on top because we have the flexibility to be able to do so without causing any disruption to the storage layer.
So we've gotten into like the roots of Vast, and this is like the really the infrastructure that Vast is built on, which we talked a couple of years ago in Manhattan, and basically you talked about how this is a much better alternative to Hadoop on the one end and S3 on the other, way faster, based on SSDs. But obviously, Vast has gone through a pretty big pivot over the last couple of years since AI became a thing. And so, what was the moment when Vast said, "Hey, we don't need to stay in this storage layer, building the best possible storage for big data type queries or Spark queries, we can move up the stack and have a new thing to contribute"? Was it a single moment, or was it kind of a gradual evolution looking at the environment and what users and AI users were interested in?
We always intended to go as far up the stack as
Mm-hmm.
possible. But in the beginning, you have to start with something basic that
Makes
everybody
sense.
needs. And so, what everybody needed was large scale, high performance, cost efficient storage at the very beginning. And the reason that we entered that market as opposed to entering at the database level or at the application level was because we obviously had deep roots in that, but we also knew that if we started at the foundational level at the hardest problems, because the problems that we solved initially were very hard to solve. But because the architecture we created was so unique and so different, we were able to solve them in ways that people hadn't thought of before. But we solved the hard problems first. And I'm not going to compare ourselves to Amazon directly, but if you think about AWS's initial service offering, it was storage, it was
hmm
S3. And once you have the data, you can start to do things on top of it and you don't need to move it somewhere else. And so what happened was we received all of this data from all these customers. All these customers would deploy large scale systems and they had a place to store it. But we started noticing that their applications, in some cases, weren't performing as well as they wanted to. And so we started realizing that there was an ability for us to move up the stack more immediately. We always focus on where the customers bring us to. We have visions that put us out 5, 10 years in the future, but the truth of the matter is that we only get there if there's customers who are willing to go with us on that journey. And the initial set of customers, they needed us for storage, but over time, they wanted to start adding more applications on top because they were spending too much money on other services where we could find a way to make them better. And so we started with the storage layer. We moved into what we call the database layer, but database, to be honest, is just another word for storage. It's a different way of storing data,
hmm
right? And so you have unstructured data, you have structured data, which is also all the derivatives from the unstructured data. And then what you need is a processing engine, processing layer, right? So we started with the data store. We have the database, which sits alongside of it. And then we created the data engine, which is basically the ability for applications to run on the platform and process the data that lives in it without having to go outside, without having to push it to some external system, and without having to go and use another system to store any of its state. So all of the tables, all of the associated metadata, it all goes into the same platform. So you don't need to move it out.
Right. So basically, you've built a better mousetrap, and basically, I mean, one can be jaded about all that, except for the fact that we take a look at your remarkable growth. I'm going to ask one final question just to go out here, and of course, we'll have to come back and continue the conversation. But it seems like that elsewhere in the data world, that S3 seems to be becoming kind of a default, kind of like a default go-to. And the fact is that S3 has come a long way since its early days. It's just raw object storage. We're seeing it basically becoming the default for lake houses. So where do you see yourselves basically existing in this landscape, given that S3 has become kind of like the new normal, and with the emergence of lake houses? Where do you see yourselves playing? Tell us.
Yeah, so I think, and it actually goes beyond the lake house. That
Mm-hmm.
the concept of using S3 object storage for doing large scale analytics, it actually goes back almost a decade, where people were starting to use AWS S3 alongside EMR
Right.
to do processing in the cloud, because people weren't building HDFS file systems in the cloud. There was no reason to. They already had S3;
Right.
it was sitting there. But we started seeing it more and more where the table formats themselves were being designed around object storage.
Mhm.
And so we did find ourselves a market there. But we also found ourselves an opportunity there to improve upon what those table formats had done. Like the Lakehouse table formats are all focused on using S3 object storage, which intrinsically is not well suited for a database, because you can't modify objects in place. But we built our own structures. We can do whatever we want to them. And so when we created our database, we actually had the Lakehouse concepts uh, top of mind, because it allowed us to make a much better optimization layer for running those kinds of large scale analytics. Now, the good news is that whether you want to use an existing lakehouse technology like Delta Lake or Iceberg, you can do so on top of VAST using us as, for lack of a better term, the dumb object storage. But you can also transition the high churn tables or the high performance tables over to VAST database without having to change your code. And you can do processing in place on our platform using either Spark or Trino directly on the nodes of the cluster, in addition to using what we call our data engine functions and query engine to
Mhm.
run those same types of analytics. So we basically, like, if you think about the mousetrap that we've built, over time, you will see a lot of, I would say, parallels to the way that a lot of the cloud service providers have built their offerings, where they start with the base layer and they start to add services. So we've added most of the services that are necessary for doing all the processing and managing of data on a platform. And so that's kind of where we see it. Whether it's Lakehouse, whether it's doing AI model training and inference, whether it's doing even whether it's just basically doing basic processing or ETL, like all of those things can be done directly on the platform without having to go and use external systems. So our goal is to try and bring as many of those workloads into VAST as possible.
Well, thank you so much. This has been a really exciting conversation, and I'm looking forward to seeing where you guys go in the future. Maybe one very brief closeout question, which is, if I come from a data engineering background. If a data engineer wants to get hands-on with something from Vast, just wants to try it out, is there a way for them to do that?
There actually is. It's getting. At first, it was difficult,
Yeah,
but I will say that. So there's two options people have. One is we have a community called the Cosmos community.
yeah.
So if you go if you search for it online, you can find it. You can actually get hands-on on a system without doing any special tricks. You can just log in with whatever credentials you want, and you can get onto a system. We'll be expanding the capabilities of that over time to make it easier and easier for people to get sort of jump started. You can also deploy VAST in the public cloud in AWS and GCP. Azure is also soon to follow. So it's very easy for people to get started. But if you want a no cost, zero friction way, you can just go to a Cosmos community and do it that way.
Excellent. We'll put a link in our show notes. And yeah, like Tony said, we hope to have another conversation with you guys, because I imagine this raise is a really big deal in terms of what you're building. And so probably see a lot more announcements in the next 6 months or year.
Right. And we
Thank
haven't
you.
even got into your whole AI control, layer. So
Exactly.
we definitely have another conversation there.
Scratching the surface.
Yeah,
Yeah.
exactly. Sounds good. Thanks very much for joining us.
Thank
Thank
you.
you.